Let's get you back.
Okay, folks, it is that time. So I am going to go ahead and get started. So today what we're going to be talking about is so what we discussed the last 3 classes of lecture has really been the mathematics, some of the basics to the mathematics that we use on a regular basis. We've talked about significant digits and how measurements need to be recorded to the correct number of significant digits. We've talked about the fact that measurements must have a value and a unit. We've talked about the fact that we can perform calculations with values, and specifically we focused on how to record the answers to those calculations to the correct number of significant digits. If you're dealing with multiplication and division, the answer will have the same number of significant digits as the measurement with the fewest. If you're dealing with addition and subtraction, the answer will have the same number of decimal places as the measurement with the fewest decimal places. These are tools that we use on a regular basis. We then went on and I introduced the metric prefix system, because in chemistry, we do tend to use more of the metric system rather than the English system. And the reason we use the metric system is because it is known worldwide, whereas the English system is used in limited countries. So we did focus on the metric system. And then on Monday, we talked about how to perform calculations, primarily with the metric prefix system. And for Monday, the main focus was getting down the process of doing a calculation and recording the answers to the correct sig figs. So when we're dealing with a reading problem, you're going to be given a piece of information and you're going to ask to convert that into a new unit. So you identify what you were given. You identify what you want to solve for. The next thing you do is look for similarities in the unit. If there is something in common within that unit's names, that's when you're going to be using your metric prefix system. But if the 2 units do not have anything in common name-wise, that's when you'll use the English to metric system. So we identified what we wanted. We identified what we wanted to solve for. We identified the system, English or metric, that we would need to obtain our conversion factors for. And then we talked about the process of conversions. And when you deal with conversion, you start with the quantity that you were given. Your first conversion unit is going to have the unit you wish to get rid of in the denominator. And then the other part of the equality in the numerator. And you can have, I've seen conversions that have 10 conversion factors. You can have more than, and there's more than one way to put in conversion factors, but the key to conversion factors is you pay attention to your units as you go along so that they cancel. We will be performing conversions a lot for the rest of the semester, but we will be getting more into the chemical conversions rather than into just general conversions. Now today, what we're going to do is we're going to talk about one more thing that is related to the calculations that we will be performing, and that is we're going to get into formula mass, molar mass, Avogadro's number, and we'll also talk about the mole to mole ratio. These are going to be important factors that go into stoichiometry, which is the mathematics for chemistry, where we're converting from one chemical into another chemical. So before we just converted units, now we're going to get to converting chemicals too. Okay, so back around the time of the first exam, one of the things that we discussed was how to come up with the average atomic mass of an element. The average atomic mass is what is represented in red on the periodic table on the wall. In other words, it's that lower number. The average atomic mass was equal to the sum over all naturally occurring isotopes of the isotope mass times the abundance. So basically, this is where we find out that oxygen is 15.9994. This is where we came up with the value for hydrogen as 1.007 and so on. This is where we come up with the value that carbon is 12.011. Now, the unit for average atomic mass was the AMU, where AMU stands for atomic mass unit. So hydrogen has an atomic mass unit of 1.00794. Oxygen has an atomic mass unit of 15.9994 AMUs. Again, that value is the result of determining the average atomic mass. Now, it has only been within the last 30 years that we have developed technology capable of seeing a gold atom. And gold is actually one of the largest elements on the periodic table. But it's only been within the last 30 years that we could see a gold atom. We cannot manipulate them. So this particular method where we talk about the atomic mass unit, we're talking about one atom of hydrogen, and we cannot manipulate one atom of hydrogen. For our oxygen, we're talking about one atom of oxygen. We cannot manipulate one atom. So how can we do the chemistry? Well, there was an individual by the name of Lorenzo Romano Amadeo Avogadro di Querna e di Cerreto. No, you do not need to know his name. Better known though as just simply Avogadro. And Avogadro did some studies. Specifically, he focused on carbon. But basically, what it boiled down to is instead of having 1.00794 AMUs, if instead we had 1.00794 grams, something we could measure, what does that mean? What that means is if we have 1.00794 grams, then we have 6.022 times 10 to the 23rd hydrogen atoms in this case. For oxygen, if instead of talking about 15.9994 AMU, we talk about 15.9994 grams. Now we have 6.022 times 10 to the 23rd oxygen atoms. This number, 6.022 times 10 to the 23rd of anything, is equal to 1 mole of that thing. And it is known as Avogadro's number. So we know that 1 point from his work, we know that 1.00794 grams of hydrogen is equal to 6.022 times 10 to the 23rd hydrogen atoms. And we know that 6.022 times 10 to the 23rd of anything, in this case, hydrogen atoms, would equal 1 mole of that thing, in this case, hydrogen. So putting those if-then statements together, it means that 1.00794 grams of hydrogen must equal 1 mole of hydrogen. The same thing goes for our oxygen. We know that 15.9994 grams of oxygen is equal to 6.022 times 10 to the 23rd oxygen atoms. And we know that 6.022 times 10 to the 23rd of anything, in this case, oxygen atoms, is equal to 1 mole of that thing. So what we can deduce if you take the two if-then statements into account, is that 15.9994 grams of oxygen has to equal 1 mole of oxygen. So I said we were going to talk about formula mass. Molar mass. And Avogadro's number. They are all related. So for, let's see. Let's take magnesium. For 1 atom of magnesium, it has a mass of 24.305 AMU. We know that because that is what's on the periodic table. That is its average atomic mass. Now, if you take, instead of having just one, you take it up to 6.022 times 10 to the 23rd of them, then 1 mole of magnesium is going to weigh 24.305 grams of magnesium. Scandium. 1 atom of scandium has a mass of 44.956 atomic mass units. But if we take and go to 6.022 times 10 to the 23rd, then we're going to have 1 mole of scandium. And that's going to have a mass of 44.956 grams of scandium. So what we can say is that the formula mass is associated with 1 unit of the substance and it has a mass in atomic mass units. Avogadro's number specifically says that 1 mole of anything is equal to 6.022 times 10 to the 23rd of that thing. And then you finally have molar mass. The word molar contains moles, just like the units, and it contains the term mass, which is what gram measures. So it's called its molar mass. The molar mass, therefore, is the mass in grams of 1 mole of substance. The two numbers are identical. The values, I should say, the values are identical. The only difference between them is what they're talking about. Is it just a single entity, or is it 6.022 times 10 to the 23rd of that entity? Avogadro's number, folks, is a counting number. Just like you count out 12 eggs to get to a dozen, to get to a mole, you can count out 6.022 times 10 to the 23rd. It's just a counting number. So folks, if I asked you for the formula mass of lead, you look at the periodic table and it's 207.2 and you attach AMU. If I ask you for the molar mass of lead, you look at the periodic table and go, it's 207.2, but now it's in grams per mole. Any questions about the difference between, for an element, the difference between a formula mass and a molar mass? And what they mean? Okay, so now let's move on to talking about our compounds. We've developed the formula for compounds. Let's move on to talk about those. Chemistry follows the law of conservation of matter. The law of conservation of matter says that matter cannot be made nor destroyed. Cannot be created, nor can it be destroyed. Now, matter which I believe was early. Matter is anything that has mass and takes up space. So even though we cannot touch an atom of a hydrogen because it has a mass, it is matter. Just because we can't hold an atom of oxygen because it has mass and it takes up space, it's considered to be matter. Understanding that is important because matter cannot be created, nor can it be destroyed. That means an atom of oxygen cannot be created, nor can it be destroyed. The oxygen is already there. It may be in a different format. Maybe it's in carbon dioxide, but the oxygen's already there. We didn't create it. We can't, we're not destroying it. It's already in existence. And if an atom of oxygen cannot be created nor destroyed, and an atom of oxygen has its own mass, which it has to because it is matter, that means that the mass of the oxygen is carried with it when making compounds. Now, obviously, I used oxygen as my example, but I could have used hydrogen. I could have used nitrogen. I could have used radon. I could use any element up there. The fact of the matter is in order for us to follow the law of conservation of matter, since matter is anything that has mass and takes up space, it means that that element has to carry with it its mass in making a compound. So if I look at a compound such as carbon dioxide. Carbon dioxide has one carbon atom and it has two oxygens. According to the periodic table, carbon has a mass of 12.011. It has to carry that mass with it. Oxygen has a mass of 15.9994. It carries that mass with it. So carbon contributes 12.011 to the overall mass of carbon dioxide. And since there are two oxygens at 15.9994 each, that means that they carry 31.9988 with it. So carbon dioxide has a mass of 44.0098. and for its value. Now, what that means is if I have one carbon dioxide molecule, then the mass is going to be 44.009. Actually, it would be 44 point, because I got to round up to keep my sig figs, 10 AMU. But if I have 1 mole of carbon dioxide, then it's going to have a mass of 44.010 grams of carbon dioxide. Again, this top one would be the formula mass. The bottom one would be the molar mass. And the difference is we went from 1 atom or 1 molecule to 6.022 times 10 to the 23rd of them. Questions so far? It's not going to get a whole lot tougher. There is one type of problem that would be tougher. But for the most part, it's not going to get a whole lot tougher to go from formula mass to molar mass. Let's do one more simple one, and then I'll do a couple that are a little bit tougher, and then we'll move from there. So let's take glucose, C6H12O6. Which you frequently talk about with respect to respiration. C6H12O6 has 6 carbons, 12 hydrogens, and 6 oxygens. Each carbon brings with it the 12.011 AMUs. Each hydrogen brings with it 1.00794. And each oxygen brings with it 15.9994. So since you have 6 carbons, each at 12.011, that means that the carbons contribute 72.066 to the overall mass. Since you have 12 hydrogens at 1.00794 each, that means the hydrogens contribute 12.09528 to the overall mass. And since you have 6 oxygens at 15.9994 each, that means that the oxygens contribute 95.9964 to the overall mass. When you add these together, you get a mass of 180.15768. So in other words, if it is 1 molecule of glucose, then it's going to have a mass of 180.158 AMU. But if we are talking about 1 mole of the material, then it's going to have a mass of 180.158 grams for that glucose, for that mole of glucose. Questions? So the harder question is actually the questions that involved more than one polyatomic ion. So let's take Ca3PO42. You have to remember what this actually means. It means you have 3 calciums, 1, 2, 3, and you have 2 PO4s. So if we're making our list, we're going to have 3 calcium atoms. We're going to have 2 phosphoruses, and we're going to have 8 oxygens. Calcium has a mass of 40.078. Phosphorus has a mass of 30.974, and oxygen has a mass of 15.9994. So your calciums contribute 120.234 to the overall mass. Your phosphoruses contribute 61.948, and your oxygens contribute 127.9952. When you add those together, you get a mass of 310.1772. So in other words, one molecule of Ca3PO42 has a mass of 310.177 AMU. But if we're talking about one mole of our calcium phosphate, then we're talking about 310.177 grams of the calcium phosphate. Questions? Yes.
For the mass for phosphate, well, it has more numbers on the periodic table. Why did you find out?
It all depends upon what periodic table you use. Some of them only have 2 decimal places. This one, most of them are to 3 decimal places, but not even all of them are on here to 3. So it's really dependent upon what periodic table you're using. And since I can't read those numbers over there, I went with what I could. Okay, that's actually a very good question. Will it affect the answer? If you round too drastically, it affects the answer. But as long as you're barely rounding, it's in like the 3rd decimal places, usually it's not going to affect the answer much. It's only if, and I always give leeway as long as it's mostly correct, because again, it is dependent upon the periodic table. On your active, so with active, when you click the plus sign at the bottom, it will pull, one of the options is a periodic table that it can pull up. And so you can use their values directly from their periodic table. So again, on active, if there's a plus sign at the bottom, if you click on that plus sign, it'll pull up the option for periodic table or OpenStax. If you click on the periodic table, you can use their values. Questions about this? This is the homework for today. What I'm about to do is not homework for today, but it's going to be homework eventually. Because I have just now given you some new conversion factors. I'm going to give it out as you leave. Here. I just forgot. And I think I did get it posted. I kept trying to get it posted yesterday, but it's here. Yes.
We have to remember the metric to English for the test.
No, you only need to remember the metric to metric. So what you got to know for the test is the metric. You got to know 1 milliliter is equal to 1 cc, or same thing as 1 milliliter is equal to 1 centimeter cubed. And you got to know that 1 angstrom is equal to 1 times 10 to the minus 10 meters. The only other ones you got to know are like seconds. I won't give you time because it's time. And I won't give you 12 inches to a foot, things that I think you should know. But basically the table I'm about to hand out, that's what you're going to get. You've got to know the metric to metric. So yes, you got to know the tera, giga, mega, kilo conversions. Yes. It's just a little circle. Kind of reminds me almost of the Anaheim Angels. Is it the Anaheim now? Baseball. I'm a baseball fan. And it almost reminds me of the halo on the Angels. Okay. But it's just a circle. I would have to guess that the reason there is probably where they came up with the term angstrom from. I want to say it's a German or one of those languages, and it probably came from the language it was from. Just like if you get certain words, you'll get the umlaut and stuff like that. Like resume, you get the little hyphens above the E's. It's for the same reason. Okay. Now, you're going to get new conversion factors, but you're not going to memorize these. These are the ones to remember. But we now have new conversion factors that can be developed. The first one is the molar mass. We just talked about that one. The molar mass is used to convert mass into moles or vice versa. A second conversion factor that we can use that can that we've developed is Avogadro's number. You do not have to memorize Avogadro's number. It will be on a formula sheet. But you will use Avogadro's number to convert between moles and the word ions, molecules, or atoms. The final conversion factor we really haven't talked about yet, but we're about to, is known as the mole-to-mole ratio. Mole-to-mole ratios are used to convert between two different substances. Now, one of those mole-to-mole ratios, we're going to talk about the first one now. There's actually two. We're only going to talk about one now. And one of those mole-to-mole ratios is found within a chemical formula. Basically, the subscripts are the key. So an example would be if I have H2O, which is water. For every 1 mole of water, you have to have 2 moles of hydrogen, and you have to have 1 mole of oxygen. Now for our calcium phosphate that we did earlier, for every 1 mole of the calcium phosphate, you had 3 moles of calcium, 2 moles of phosphorus, and 8 moles of oxygen. And if you look back at where I calculated calcium phosphate, you will see I multiplied the mass by those particular numbers. That's where it came from. So we are going to be using these conversion factors for the remainder of today and probably a little bit on Monday. So Monday's homework is going to have some of these calculations involved. So what I will be doing is I'm going to teach you how to interpret these problems, how to identify what conversion factor you need at each step along the way. So let's see. How many molecules of calcium phosphate are found in 24.696 grams of calcium phosphate? I'm going to use very similar processes that I used with the metric. Step number one, I'm going to identify what I was given. I was given 24.696 grams of calcium phosphate. Next, I'm going to identify what I want to solve for. I want to know molecules of calcium phosphate. Now here is actually where it's a lot easier to a large extent than what we were doing with the metric system. First thing I note, the first thing I always look at is going to be the substance. What I note here is that I am working with the same substance so no mole to mole ratio is going to be needed. If you go back up, when I talked about the different types of conversion factors, I said if you had that one of them would be a mole to mole ratio, and you would use it if the substances were different. So since they are the same, it means no mole to mole is necessary. The next thing I see is I have grams. Grams typically means I will need the molar mass. Which we calculated earlier as 310.177. The other thing I notice is that I have molecules. And anytime I see molecules or atoms or ions, You're going to go to Avogadro's number. So one of the conversion factors I am going to need is 6.022 times 10 to the 23rd of anything is equal to 1 mole of that thing. So just like before, I would look at things and determine where I needed to find my conversion factors. Earlier, I said if it had something in common name-wise, go to the metric system. If it didn't have something in common, go to the English go to the English system. Now I'm telling you, if you're dealing with a substance, a compound, or an element, there are 3 conversion factors that you go to: mole to mole, Avogadro's number, and molar mass. And it all depends upon what you need, is based off of what information you have going back and forth between these. So now to do this math, I started out with 24.696 grams of calcium carbonate. Calcium phosphate, excuse me. My first conversion factor, just like before, we're always going to start with, I need something that's going to have the same unit to cancel out. Now, here is one new facet. Not only does it have to have the same unit, but it's got to have the same substance. Today, for this question, that's not important, but for future questions, it could be. So again, not only does it have to have the same unit, but it has to have the same substance involved. So I need grams. I'm going to use my molar mass of 310.177 grams of calcium phosphate is 1 mole of calcium phosphate. Because my grams and the substance has to cancel out. The grams and the substance has to cancel out. Next, I now have moles, but I wanted molecules. So now's where I'm going to use Avogadro's number. 1 mole of Ca3PO42 is going to have 6.022 times 10 to the 23rd Ca3PO42 molecules. Keying this into the calculator, I get 4.79466 times 10 to the 22 Ca3PO42 molecules. Now I do have to pay attention to significant digits. This is multiplication and division, and according to the rules of multiplication and division, your answer should have the same number of significant digits as the measurement with the fewest. Your starting quantity had 5 significant digits. The mole portion of molar masses are exact quantities. The mole portion of molar masses are exact quantities. The mass portion had 6 significant digits. The Avogadro's number here has 4 significant digits. And again, the mole portion of Avogadro's number will be an exact quantity. So you have 5 significant digits times an unlimited number of significant digits divided by 6 significant digits times 4 significant digits divided by an unlimited number of significant digits. The measurement with the fewest had 4, So our answer should only have 4. So you should record this answer as 4.795 times 10 to the 22 calcium phosphate molecules. Questions? Let's look at another one. How many oxygen atoms are in? Let's go with 29.61 grams of carbon dioxide. You start by identifying what you have been given. I have been given 29.61 grams of carbon dioxide. Identify what you want to solve for. I want to know oxygen atoms. First thing I note is that I have 2 different substances. Whoops. Have 2 different substances. Because I have 2 different substances, I will be using a mole to mole ratio this time. Have to use a mole to mole ratio this time. According to the formula of CO2, for every 1 mole of CO2, there are 2 moles of oxygen. Had to use a mole to mole ratio in this case because we are dealing with 2 different substances. The next thing I note is that I'm dealing with grams. Grams means I'm going to need the molar mass. Which we calculated earlier as 44.01 something. I'm going to go look it up so I don't have to recalculate today. 44.010. And last thing I note is that I'm dealing with, keep doing that. Last thing I notice, I'm dealing with atoms. So I'm going to need Avogadro's number. Which in this case will be 6.022 times 10 to the 23rd. Oxygen atoms is equal to 1 mole of oxygen. Yes. Because the question didn't have carbon in it. It only asked for oxygen and CO2. If it had asked for how many carbon atoms, then I would have played with the carbon instead. So in other words, I could easily have written the mole to mole ratio as 1 mole of carbon. But again, because but when I get to the actual problem, I only need this portion of it because the oxygen and the CO2 were the only things in the actual question. So now to begin this calculation, I start with the 29.61 grams of carbon dioxide. My very first conversion factor has to have grams of carbon dioxide, so I'm going to use the molar mass as my first conversion factor. I'm going to place the 44.010 grams of carbon dioxide in the denominator with the 1 mole of carbon dioxide in the numerator. The grams of carbon dioxide were placed in the denominator because I needed the unit and the substance to cancel out. Now I have moles of carbon dioxide, but I need to get to oxygen. So my second conversion factor is going to be the mole to mole ratio. Of that mole to mole ratio, I'm going to place the mole of carbon dioxide in the denominator with the moles of oxygen in the numerator. The moles of carbon dioxide went into the denominator so that the unit and the substance would cancel out, leaving moles of oxygen. But I need atoms of oxygen, so I'm going to use Avogadro's number as my third conversion factor. On Avogadro's number, the mole portion will go into the denominator, whereas the 6.022 times 10 to the 23rd oxygen atoms will go into the numerator. The mole portion had to go in the denominator so that the unit and the substance would cancel, and I was left with the oxygen atoms. So keying that into the calculator, you get a value of 8.103222 times 10 to the 23rd oxygen atoms. This is multiplication and division, and according to the rules of multiplication and division, your answer will have the same number of significant digits as the measurement with the fewest. Your starting value had 4 significant digits. The mole portion of a molar mass is an exact quantity, but the mass portion you have to pay attention to. Mole to mole ratios are exact quantities. The Avogadro's number had 4 significant digits, and then the mole portion of Avogadro's number is an exact quantity. So the measurement with the fewest had 4 significant digits, so our answer can only have 4. So we would record this answer as 8.103 times 10 to the 23rd oxygen atoms. Questions? For today's homework, like I said, you're doing molar mass. We're going to pick up with more of these on Monday before you have to do the homework on these. But you're going, and also folks, I will be posting at some point, probably next week. I have a gazillion videos that do one problem at a time, so you can watch as many as you need or as few as you need, and I walk you through these same exact steps. So I will see you on Monday. If here's a conversion table to come pick up.